Good afternoon, everyone, and welcome to another great webinar, a weekly webinar that's hosted by the Connecticut Center Advanced Technology for NERDIC, which is the New England Regional Defense Industry Collaboration. Those of you new on this, I'm going to explain a little bit more about NERDIC later, and you're going to hear from some other folks, but it's been a great organization, a great collaborative organization throughout New England. So we've got an exciting presentation today, technology demonstration about model-based definition. This is something hopefully you've been hearing a little bit more about, certainly one of those things around Industry 4.0 that's going to be really vital going forward for a lot of companies, but not just vital from the standpoint of it's something that you're being required to do from an OEM or even a government entity, but it just makes good business sense. It's a phenomenal method to be developing parts, and you're going to hear from Mitch Kaminski and RAM and his folks about that later on. Before that, we're going to hear from Colin Cooper, and again, great agenda. So give you a little bit of overview, very briefly about NERDIC. Go to the next slide. NERDIC has been around for a few years now, and again, just New England regional. And it's something so important because we talk about this a lot, about pulling our resources together, understanding that borders don't really matter much. We've got to understand what assets we have on a regional basis. Certainly our OEMs, our global industrial companies, and a lot of the federal defense contractors obviously have operations all over the place. So how we leverage our educational resources, leverage the MEPs, the manufacturing extension programs accordingly, all of our educational resources, our technology centers like CCAT and the others, all these things just vitally important at this time to pool these resources together, understanding what everybody's doing, and really have a vision and focus to drive our industry forward. NERDIC is doing that, creating this ecosystem around Industry 4.0 and some of the more valid technologies that we see that are most important, most vital to our industry segment. So you see the kind of model for NERDIC. We show this slide very often, and as you look at it, NERDIC's in the center, but you look at those outward circles there, and you've got all the major players, the pieces of the puzzle that need to be in place again to drive this industry segment forward, and then some of the breakdown of the technology. So a great segue into Connecticut's Chief Manufacturing Officer, Colin Cooper, who's going to come on. Colin is very much involved with NERDIC on a NERDIC basis, but knows everything manufacturing-wise. We just actually were on a webinar this morning, Colin and I, so we go from one thing to another. And Colin, it's about all of these resources, pulling them, getting the small manufacturers to understand what's out there. And I guess you can't do it enough. You have to be doing it almost every day. But love to hear some of your comments, and then you and I can chat a bit.
Yeah, great. Thanks, Ron. Good afternoon, and good afternoon, everybody. And Ron, thanks for having me. This is, you're right, it is all about awareness. There are tremendous assets available to help people throughout New England, and seminars like this, webinars like this, really just help people understand what's available. So welcome to this week's session on Industry 4.0 technologies. As Ron said, I don't need to give a lot of background about NERDIC. Ron did a great job of explaining. It's a Department of Defense backed organization consisting of government and private sector representatives from all 6 New England states that work together to strengthen our regional defense industrial supply base through advocacy and programming. In addition to this series on Industry 4.0 technologies, last year NERDIC established a cybersecurity training program, partnering with the New England Manufacturing Extension Partnership Centers, led by CONSTEP. So many thanks to CCAT and the team there for developing and launching these Industry 4.0 technology workshops and demonstrations. The Department of Defense is keenly interested in fostering the adoption of new digital technologies in the defense manufacturing supply base. And the first step is an awareness of these technologies and the transformational power they represent. The sessions at CCATs, I've been fortunate to participate in a number of these, and I can say that the ones that I've seen to date have been very interesting and informative, and led by subject matter experts, and you'll see that today with Mitch and his team. Today's presentation We'll demonstrate the power of model-based definition and some of the cost-saving attributes, which is always something of interest to suppliers. Model-based definition really is a foundational digital technology that will become a requirement for next generation DoD programs. So it's great that you all tuned in today. And as I'm sure, Ron, you'll let people know, CCAT has additional technology demonstrations scheduled through the month of August, which we encourage everybody to tune into. So thanks to everybody for participating, and I'll turn it back to you, Ron.
Thanks, Colin. And you see on here we had those some great partners. But Colin, I'm going to kind of throw you off base for just a moment because you grew a pretty tremendous company, Woodcraft, over the years. And you look at model-based definition coming on right now, and these digital thread technologies. If you were back in your previous seat, this was something that I think you probably had already embarked on or started to in some degree, but as a manufacturer, because that's really what we're trying to play to right now. How important is this, not having your chief manufacturing officer hat on, but your business owner, your manufacturing hat on?
Yeah, this whole digital transformation, it was really, I've been with the state now for almost 2 years, and this was something that I was just becoming aware of, model-based definition, as I was sort of winding down at Woodcraft, and actually it was in some conversations with Mitch, who's going to be on today. And really understanding what it was all about and what the power of it was. As you know, in Industry 4.0, there's a host, about a dozen different technologies, and not everything works for everybody. They have to figure out sort of what their business model is and where they can best leverage it. It's a difficult thing for a lot of business owners and business leaders to get their arms around, because a lot of this stuff is sort of knowledge-based processes. It's not like investing in a new machine that's got faster feeds and speeds, and it's pretty easy to do the ROI calculation. Here is changing the way we do things. But again, and that's why events like today, where you really talk about and give some examples of how people are utilizing this technology. We've always found that the technology gets adopted when other business leaders see how other businesses are using it, and say, hey, I can use that in my business this way. And so the first step in this transformation really is awareness. And that's what this is all about, building awareness. And then you start to, when people start to understand what's available out there and start to understand, they know what they don't know, then they're incentivized to go and learn about it. And then ultimately, go through the process of adopting these technologies. This is, again, one of many different new digital technologies that are coming to the fore, but this really is a foundational technology. So it's key. It's going to be, as you mentioned earlier, it's going to be a requirement for DoD suppliers, but it's also good business practice for anybody who's in manufacturing. And you're starting to see it really spread in industries like the auto industry and whatnot. So it's coming across a broad front. And again, for people tuning in today, again, the first step is just an awareness of what this technology can do for you. And then, then plugging into places like CCAT on what you're doing and working with you all to actually start moving and adopting this technology. So, so this is great. We're happy to be part of this, and looking forward to listening to Ram Engineering's presentation today.
Well, we're also fortunate, Colin, obviously, to have you sitting where you are right now, to have that decades of manufacturing experience now at the state level. I like to think a lot of these programs that we're talking about, this one in particular today, regarding Industry 4.0, without the leadership of the MIF board and moving these, I mean, the foresight is pretty amazing. I mean, that's the beauty of where we are today is you don't have a crystal ball several years ago, and here we are today, and we've got these programs in place, active, tremendous resources. We just have to keep getting that message, like you said, the term awareness. We just can't do enough to make the companies aware of these programs.
Right, Ron. As you know, the manufacturing supply base is a mile wide and an inch deep. The manufacturing ecosystem is populated. 98.5% of manufacturers in the U.S. are characterized as small businesses. So they don't all have the resources to go out and investigate all of this and do their own due diligence. So having an organization like NERDIC to plug into, having somebody like CCAT to plug into, or Constep on the cybersecurity side, it's just a real asset. It really it buys down the cost to adopt these technologies, and it really accelerates the adoption. So again, I hope people find this interesting today, and then I hope they follow up this by actually, moving into the deployment phase.
That's great, Colin. Thank you very much for taking the time this morning, and we'll keep moving along through the presentation. So thank you, Colin. So again, we've got the model-based presentation up. I think Mitch Kaminski will bring Mitch on. Mitch is the president of RAM Engineering. Mitch has got 12 plus years as a tool designer, 25-year aerospace manufacturing engineer, great depth in the manufacturing technology space, and just an excellent presenter here on the model-based definition. So Mitch, if you can get your camera working. The other thing I want to remind everyone is that all of this today will be available in handout form. We'll be sending this out. If you've got questions, you can go right into the chat room, and we can make sure that you get those questions answered and you have access to the information. So Mitch, we'll still, I guess we'll be on hold for you. I've got your slides, but I don't know if I'm going to be qualified to give the presentation on your behalf. So we'll hopefully keep waiting, and you will pop in shortly on this. So, as Colin said, touched on it briefly, these programs, a lot of Industry 4.0 programs, no one size fits all, and all these different types of manufacturers that are out there. So there are many digital thread technologies. Model-based definition is a term we use, but there are different types of software, things that can be used throughout the model-based definition process. And when Mitch begins his presentation, you'll see as you begin to design a product, it's no longer designing a part, I should say, and just kind of letting it go through the manufacturing process and then in quality control and inspection, but all up front, you're building these manufacturing parameters in, and you're building the quality control and inspection in. So it really is a cost savings, a savings to companies that is going to be very, very vital to them going forward. So have we heard from Mitch yet? Eileen, what's up?
Hi, Ron. I think we're going to move ahead with the beginning of the presentation. Maybe Mitch is having some technical difficulties, okay. So I think we're going to be able to start with the next part. So Donna, if you could move ahead with that, I would love it. And Ron, thank you for helping us through this.
Okay, thank you.
All right, hello. Welcome to the presentation. This is a deeper dive of the presentation that we gave previously on June 11th. This is about a 45-minute presentation, so I'll go through these slides relatively quickly, and hopefully that should leave enough room on the end for questions and answers. So once again, my name is Mitch Kaminski. I'm president of RAM Engineering Solutions. We provide CAD support services to the aerospace and defense industries. We specialize in tooling design to eliminate setup, tooling design for cost reduction in manufacturing, and tooling design for cost reductions by utilizing advanced or emerging technologies. Some background on myself. I've been a manufacturing engineer for 25 years, and I've been a SolidWorks user since its inception in 1997, and I hold a CSWP, or a Certified SolidWorks Professional certification, and I've been running RAM Engineering for about 12 years now. With me today is Stephen Bukowsky. He's one of our lead design engineers. He's been a mechanical and manufacturing engineer for just over 12 years, and he's been using SolidWorks since 2004. And he also holds a CSWP, as most of the people on our staff hold CSWPs. So this presentation we've broken up into two parts. Part one is a broader overview or highlight on MBD, and it highlights how companies can save time and money over traditional drafting. And part two is a deeper dive into 3 different examples of tolerance schemes to illustrate that there is not one size fits all solution for tolerancing. So as a quick overview or recap of MBD, again, this is an extension of our previous presentation. MBD, or model-based definition, in its most basic or simplest form, is the application of product information on the CAD model itself. On the bottom left is a 3D model with MBD on it, and on the bottom right is the same 3D model but shown in a 3D PDF. For this presentation, we're going to be talking about MBD with the model, and we're going to be focusing on the application of the MBD on the model. It's worth noting here that MBD is much more than just putting PMI on the model. MBD is really the foundation or the cornerstone to a much larger paradigm shift towards a digital transformation of an organization. In many cases, MBD can be thought of as the impetus or the reason for an organization to begin its digital transformation, its transformation towards smart manufacturing. Ultimately, MBD is a shift away from, in some cases, separate legacy business systems towards a completely connected digital system. A digital system or a digital thread from when a job first comes in for quoting all the way through to when it is shipped. As we showed in previous presentations, the basic manufacturing workflow is the ability to model something with MBD, the ability to make something with MBD, and the ability to inspect something with MBD. In the optimized workflow, MBD is reused throughout the entire process. It's the reuse of this data that makes it more efficient than the alternative. The reason or the purpose to become MBD enabled is really twofold: to be more efficient and to lower costs. In prior presentations, we had discussed how early adopters of MBD are reporting time savings in the 10 to 30% range, which brings us to our first cost improvement opportunity: engineers saving time by not creating fully detailed drawings. Drafting versus detailing. On the left is a typical 2D drawing, and on the right is a typical MBD model. On the left, it takes about 30 minutes per page. It's mostly not used. In the 3D to 2D, back to 3D. On the right, it takes about five minutes to detail. It's 100% used and reused, and it's 3D to 3D. I have a brief review here that we'll run, and I believe Steve will be able to fill in some additional comments.
Right. Yeah. So this will just be a quick demonstration of what applying MBD to this particular part model looks like. So here's our part. Now you're going to see me go over to DIM Expert here. I'm using SolidWorks, by the way. And I'm going to select my 3 datum planes to begin, A, B, and C. And now I'm going to go through and I'm going to select the specific features that I want to add tolerancing information to. So I've got my clearance holes and I've got my dowel pin press fit holes. And you can see based on the strategies I have set up in my MBD templates, it dropped in hole callouts and with geometric tolerancing on there. Now I can go through and adjust the tolerance information as needed. And what I'm going to do now is add a couple reference dimensions showing the overall size of the part. This will just give my machinist the overall dimensions that he needs in order to know what size of stock to buy. These are reference dimensions because I'm not adding tolerance information there. These are, yeah, they're just for reference. So now what you're going to see me do in a moment here is I'm going to go up here and I'm going to check what the tolerance status is on the surfaces of the part right now. Everything in green has a tolerance applied to it. It's being controlled. Everything that's not in green still needs tolerance information applied to it. So what you're going to see here is I'm applying a global 20 thousandths profile of surface tolerance that will automatically apply itself to, well, it's global tolerance, so it automatically applies to all previously intolerant surfaces. So now when you see I check the tolerance status, everything is in green now. So that part is now 100% defined and ready to be sent off for manufacturing. And that only took about a minute and a half, 2 minutes and 27 seconds. All right.
So again, it's probably worth noting that this was done in real time. And if we look back at the slide, that's why, you know, on the left-hand side, we see it's about 30 minutes a page. It's pretty much an average for a standard page. When I say it's mostly not used, it's mostly used for people. There's really no computer usage in it. And you're taking a 3D model, putting it into 2D format, and then back into 3D. Whereas on the right-hand side, again, we showed it in real time. It's 100% used and reused down the process. And again, it's 3D model to 3D. I try not to call it dimensioning. It's really tolerancing. So it's directly from 3D to 3D tolerancing.
Right. Yeah. Let me just comment on that real quick. That's one of the things that I like to repeat about MBD is you're not applying dimensions to the parts. The parts are already fully defined by the model's geometry. So all you're really doing is applying tolerance information on the geometry that already exists. That's one of the fundamental differences between the 2D drawings and the 3D drawings. It's an important distinction.
Right. It's an important fundamental paradigm shift. If I can loop it back with some of the other text, it's a paradigm shift. Once you start to really wrap your head around, you know, the computer actually knows where everything is, and most of the dimensions are really for human consumption.
Right.
It's important to note that there really is no one fit answer for any particular business situation. In the end, it all depends. And in many cases, it's how those drawings are going to be used on the shop floor.
Yeah, we'll touch upon this later in the presentation as well.
So that brings us to cost improvement opportunity number 2. So opportunity number 1, we discussed how the engineers save time applying the MBD to the model versus conventional drafting. The difference is with opportunity number 2, we're going to discuss how that MBD information is reused in the 3D PDF and how that can save time as well. So with MBD on the model, the programmer doesn't have to go searching the drawing for feature information to complete his programming or toolpaths. Additionally, when a 3D PDF is on the production floor, the machinists or operators don't have to search for feature tolerances while installing features. Additionally, any dimensions that are not provided on the 3D PDF, the machinists or the operators can obtain them directly from the 3D PDF. And we're going to demonstrate that a little bit later on where some of those features are. We have a 3D PDF demonstration that we'd like to show you, and I'll run that video right now. And I'll let Stephen talk over while it's running.
Mm-hmm. Okay, so this is the same part you just saw me detail. Now what I'm going to do is I'm going to capture 3D views. So this is a very similar process to capturing 2D views like we've all done in 2D drafting. The interface is a little bit different, but the general idea is the same. So you just saw me create the top view. Now I'm going to create my front view here, just arrange my dimensions a little bit to clean it up. Go down, capture that 3D view. Okay. And now I'm going to create an isometric view. And in my isometric view, I'm going to add some notes that I have in this particular part template, which automatically populate with saw cut size, CNC prep size, material, heat treat, all that good stuff. So now that that's done, I'm going to go down here, publish this to a 3D PDF. I already have a Ram Engineering template set up. Select the 3 views that I just created that I want to show in my PDF. And now I'm going to attach a step 242 file to the 3D PDF. Hit the checkbox and save.
And again, this is all done in real time.
And here we have the 3D PDF. And this looks similar to a drawing, but it has a lot of obvious benefits, like being able to rotate your parts. I can still switch between the views that I just created. And if you look over here, attachments, there's my step 242 file, which I can save directly from this interface. So this is really your one-stop shop. You've got all of your CAD data, plus the 3D PDF itself allows you to visually see what the part is or get dimensions pulled off of it without actually being in a CAD system.
So you created all the views very similar to what you would normally do on a 2D drawing, but you did it in the 3D environment. And then you imported those captured views into an already established template. And along with that, in that process, you attached a step 242 file. It's also worth noting here that you can attach other files. For example, if you're doing additive manufacturing, you can attach a 3MF file. You can attach whatever other file format you'd like to. And what's nice is that they are attached to the PDF, so there is revision control and model control. All at the same time.
Yeah, it's nice not having to juggle multiple files. All the information contained in a single file. So this is especially helpful if you're working with an outside vendor and you need to make sure that all the files that you're giving them are the same revision or any of those sort of pitfalls that many of us have experienced.
Okay, moving on, this is where we look at the next cost opportunity, number 3, in the model preceding the drawing interpretation. So what we've experienced in the aerospace and defense industry is over the last 5 years as more computers came online and the speed of some of the product development, we've seen that the flow down requirements began to change. So it used to be the purchase order, then the drawing, and then the model. Whereas today we're seeing that the purchase order is still the overriding contract, but then the model is number 2 on the chart on the tier, and then followed by the drawing. The speed in which some of those changes can be made in some cases are faster than the POs or buyers can update the POs. This highlights the greater importance that's being placed on the models. In the case shown here, the relief that does not go through the base plate. So in this example, it's more easily spotted, but it won't always be the case. In this, what I'm trying to show in this example is that let's just hypothetically say that this is the 5th iteration or the 5th change to this model. On the right-hand side, the model knows that the relief shown in blue does not go all the way through the part. But if the tool maker had made the prior 4 iterations and on the left-hand side doesn't realize that that relief does not go all the way through, it's more easily errored to make that pocket go all the way through.
Yeah, the whole idea here is, I'm sure many of us are familiar with dealing with misinterpreted drawings and requiring rework or scrapping the parts and having to get them remade at the worst possible time. So anything that we can do to eliminate the potential for misinterpretation is of great benefit.
Yeah, the model doesn't lend itself to interpretation as a 2D drawing does. So that brings us to the manufacturing side, or cost improvement opportunity number 4, which is traditional versus digital manufacturing. And this is probably the most important slide about the costs. So on the left-hand side, we can see that we had these 2 jobs quoted, one conventional manufacturing and the other one digital manufacturing. On the left-hand side, quote number 1 has a high of 17,000 with 6 weeks ARO and a low of 7,500, 4 weeks ARO. On the digital side, on the right-hand side, on the digital manufacturing, we had a high of 6,500, 4 weeks ARO and a low of 5,000 with 3 weeks ARO. Steve, anything?
Yep. Yeah, the main distinctions with these two are the first set of quotes there are coming off of 2D drawings and going to shops that may be using manual equipment, Bridgeports. And the second set of quotes was for machine shops with 3 or 5 axis machining ability, and 3D PDFs were provided. It might not be immediately obvious in there, but a few of those parts have some somewhat complicated 5-axis features. So doing that on conventional or old school milling with sign plates and tooling balls is a lot more labor intensive than a shop that's set up to machine directly from the 3D models. Hence the large discrepancy in the quoted prices there.
So in summary, the CNC shops are able to capitalize on the CAD data, whereas the legacy conventional machine shops were not able to provide as good cost or turnaround time. So part 1 summary, cost comparison of MBD versus traditional tolerancing. Opportunity number 1, time savings with MBD over fully defined drawings. Opportunity number 2, time savings with 3D PDFs over drawings. Opportunity number 3, the model preceding the drawing interpretation. And opportunity number 4, cost of manufacturing over traditional. Anything you want to add before we move on, Steve?
No, I think we're good to move on.
So moving on to part 2 of the presentation, we'll take a deeper dive into 3 different examples of tolerance schemes to illustrate that not one size fits all solution. So here's a sample tool that we'll be discussing. It's probably worth noting, not only this tool, but the previous tool, they are real tools that we have designed for customers. And both of them were completed and delivered with customers. Stephen, anything you want to extrapolate on either the model or the BOM here?
Yeah, we'll get into this a little bit on the subsequent slide, but what you're looking at here is a simple inspection tool that's used to check thickness on certain parts. And you see the bill of materials there. This is a screenshot from within SolidWorks. The bill of materials is actually embedded in the SolidWorks assembly rather than needing to be off on a separate document somewhere. So again, I'll touch on this in a subsequent slide, but yeah, I think we're good to move on this one.
So I think in this particular case, I think it's probably a good idea that we run the video first. Let's show everybody what we're talking about when we show the 3 different schemes.
Right. All right, so once again, we're looking at a 3D PDF. These, we're going to go through the 3 main details from that assembly that I just showed you. And you'll notice here all my views are in place, ISO, bottom, top, front, right, with the associated notes. But the one thing you're going to notice with this is it looks very similar to a traditional drawing where you have dimensions on all of the features. Okay, I'll be, yeah, you can see there all of the holes have not only tolerances, but the locations are provided. Same thing here with the indicator support. You can see the full set of not just tolerances, but dimensions are applied. So this is perhaps when people are first introduced to the idea of model-based definition, and they see all the dimensions kind of floating around in space around the model. This is probably what a lot of people have in mind, and there is the expectation that, oh, it's the same as 2D drawing. only you're going to be placing all of your dimensions in 3D. And that's not necessarily wrong. It is certainly an option. And like I said, this is what that would look like for these particular parts that we're demonstrating here.
Yeah, just to recap, so we showed the assembly. We saw that on the previous slide. Right now we're looking to find details. So you see the base plate, the indicator support, and the riser block. Steve just went through all 3 PDFs. And you can see that he's fully defining them just like they would normally be defined in a 2D drawing.
Right. Okay, and pop back to our slide there. Okay. So yes, advantages, like I said before, it's just like traditional 2D drafting. It's potentially useful for organizations that are transitioning to MBD, by which I mean it's extremely similar to what everybody's already used to doing. So it doesn't require any dramatic changes in thinking. It's being a, what's that?
I was going to say, you're just applying the same dimensions that you would normally apply in your 2D drawing, but you're doing it in the 3D environment.
Right. Other advantages too is if you're in a shop that is still using manual bridge ports or lathes, but you would like to start doing MBD, as long as your the guys on the shop floor are able to see these 3D PDFs, they can still continue to work the way they're used to working. So this is potentially a good interim solution for companies that might not have transitioned to full CNC yet. Disadvantages, it's time consuming in the same way that doing full 2-dimensional drawings is time consuming. And of course, this is more effort than is necessary if you're going to eventually transition to a full digital organization. Okay.
So there's many different ways to transition from 2D drafting. We had just mentioned and shown how it could be, you can put those MBD dimensions on the model and then bring them to a 3D PDF. You can still put everything on the model and then import those model views into conventional 2D drawings. So there is an interstitial step even before going to 3D PDFs.
Yeah, again, that's true. That's worth mentioning. But
it's probably also worth mentioning that what we're showing here in SolidWorks, although that's our wheelhouse, most all of the modern CAD systems all have the same capabilities.
Right.
Move on, or you good?
Yeah, move to the next slide. All right, so this.
Again, it's probably worth us running the video first.
Yes, let's do that. All right, so what you're going to see here is the same 3-part details, or the same 3 3D PDFs, only you're going to notice now that there are a lot fewer dimensions. I've got my overall reference dimensions, once again, to let the machinist know what size stock he needs. And I have the tolerance information on my critical surfaces. But you can see it fairly clearly here. There's no dimensions except for the ones where specific tolerances are being applied. There's no whole location dimensions. And this goes back to what I was talking about earlier in the presentation. You really don't need whole locations if this is going to be fed into CAM software, because the computer knows where that hole is. It doesn't need to be explicitly told what the dimensions to the hole are. So that means that all I need to do is apply my tolerance information and let the model define itself. Once again, dimensions define a 2D drawing, but the model defines a model-based part. Adding additional dimensions to this is redundant. And what you're going to see here is this note right here that I've zoomed in on. General tolerance for all untoleranced surfaces is 20 thou profile of surface. So that means everything on that model that I don't explicitly have a tolerance called out on is globally controlled by that general tolerance. So that, of course, is a big time saving because I don't even have to worry about any of the non-critical surfaces. Not only do I not have to dimension them, but the tolerancing is automatically handled by that global profile of surface tolerance. So as you can imagine, this is a much quicker way of tolerancing your parts than having to go through and manually add dimensions and tolerances to every surface. All right.
Yeah, and just to reiterate, we were looking at the minimal tolerancing, where previously we looked at the at full tolerancing. Now we looked at the minimal tolerancing, and again, most of that those annotations that you see in the model, those are for human consumption. Again, you're going to see in the next slide how again, all that stuff is for human consumption.
Right. Okay.
So the advantages: less errors, more accurate, a typical scheme for most parts. You can have one scheme that's most applicable for all the parts. There's clearer design intent. It's just like the previously fully defined. It's exportable as a 3D PDF. And much like I said before, these minimal drawings are also still able to be captured in a typical 2D drawing. Some of the disadvantages: 2D drawings require more work. It's only intended for digital manufacturing. The minimal dimension scheme is intended for full CNC shops.
Right. I just want to clarify that second disadvantage there. The 2D drawings require more work. I'm sorry, that's the first one. What we mean by that is, let's say you are a shop that is half CNC but still has a few bridge ports, and you have a part that's toleranced like this, but the decision's made that that part is going to be made on a bridge port for whatever reason. In order to do that efficiently, you're generally going to want to generate a two-dimensional drawing for your old school machinist to work from. So that does require an extra step. Now, that said, you can take all of the MBD, all the PMI data that is currently embedded in this part, and this will very easily be dropped into a two-dimensional drawing if you need to, and then you would only need to add the extra dimensions like you would typically do on a 2D drawing. But like I said, it is an extra step. That said, if you're a full CNC shop, this is the way to go. The overwhelming majority of the parts that I've done recently have been toleranced like this. And it can be done very quickly. And as Mitch said, the design intent is extremely clear because only the things that matter are controlled, and there isn't an enormous constellation of dimensions floating around to obfuscate what you're actually trying to accomplish.
And that's what I mean by the advantages. The number two of the advantages there about a typical scheme for most parts. You'll set up your templates and whatnot that are all based to capture 80% of the parts that are going through, in this case, tool design into the tool room. So you set up a scheme that enables you to capture most of that work. And as we've shown on some of the other slides or the other videos about being able to go in there and customize anything unique that may be particular to that particular part. Good to move on?
Yeah, next slide. All right.
So just enough.
I want to talk about this one a little bit. So again, this was a project that we actually had made. So the previous two slides and videos, you saw a fully dimensioned and toleranced part. You saw, I'm sorry, the three parts fully dimensioned and toleranced. The second slide, you saw the three parts with only the minimal amount of tolerance information applied. And what you see here is actually effectively that last slide taken to an extreme. So in this particular case, the three part details are not actually broken out into separate documents. The entire assembly is toleranced as a single unit. And this, when we actually made this part, this is how I actually sent it to the manufacturer, to our machine shop. So let's play the video, and I think it'll be a little bit more clear what I'm talking about. All right, so this is what was actually sent out. The entire assembly with the bill of materials is captured once again in a 3D PDF. And I'm just highlighting the various parts in the BOM, which you can see highlights them in the viewport. That's a really nice feature. And again, this is nothing CAD specific. This is built right into your 3D PDF. As I rotate the model, you'll see my reference dimensions once again, telling my machinist what stock sizes he's going to need to buy. And you're going to see this next view here, which I've called important tolerance info. So I only have tolerances on the critical features, the dowel pin holes and the hole that the indicator stem fits in, surface flatness and perpendicularity on a couple key datums. But you'll notice nothing else has dimensions or tolerances on it. The idea here is this is a simple one-off part. I really don't care about anything other than those critical dimensions. So the entire rest of the part can be covered by that 20 thou profile of surface tolerance. And this is how the part was sent out. And our machinist had absolutely no trouble working from this one document with the embedded step 242 to provide the actual CAD data.
This same model was after it was completed and assembled, was inspected, and we found out that all the features were within print. It's probably also worth noting at this point that Stephen showed the individual details being detailed out. That's actually one model for each detail, and he had 3 different dimensioning schemes for each of those details. And then at the assembly level, he had a dimensioning scheme. This is what you're seeing here. So as he created each of those previous slides, he had 3 different dimensioning schemes for each of those parts. So you saw a fully dimensioned scheme, you saw a minimal dimension scheme, and then you saw a medium dimension scheme.
Well, this would be the minimal tolerancing scheme to taken to the extreme. So I did not even bother to tolerance the individual details. I only toleranced at the top level assembly, which again, this is just kind of highlighting the flexibility of how you can do this sort of thing. You don't have to be locked into a particular tolerancing scheme. For something like this, that's just a quick shop-made part, or something that doesn't require the same level of control that an aerospace turbine blade or something along those lines might require.
Absolutely.
Right.
So the previous tool, if you remember the previous tool that we made further up in the presentation, some of those features or some of those components could have been made in-house. Some of those components could have been made out of house. And that's where you could have applied a dimensioning scheme for your internal tool room, and you could have applied a separate dimensioning scheme for outside vendors, all within the same part.
Another interesting detail kind of along that line is you can actually have multiple tolerance schemes embedded in the same part file. Anyone familiar with configurations in SolidWorks? You can actually have different configurations, and each configuration can have its own tolerance scheme depending on whether or not the part is going to be made in-house or if it's going to be vended out, and it might need a little bit more information added. But anyway, I think you can go back to, there you go. So advantages, in this particular case, this was the fastest option because I didn't have to do any of the other stuff that you saw in the previous 2 slides. Only the bare minimum tolerances were done. Of course, it's exportable to 3D PDFs even as an assembly. And disadvantages, obviously, this is not the tolerance scheme that you're going to use all the time. But once again, just highlighting the flexibility of this sort of thing. In special cases where you can get away with it, this is a great time saver. And again, it conveys the design intent perhaps better than having the individual parts as separate details.
Very good. I'll move on.
All right.
So part two, just to summarize the tolerancing. We took a look at, on the left-hand side, we saw a fully dimensioned part in a 3D PDF, and we used a dimension scheme to match the company's needs. In the center, we had a minimal dimension scheme where 2D, I think Steve had mentioned this earlier, 2D parts are defined by their dimensions, MBD parts are defined by their models. And that's the biggest, I keep calling it the paradigm, but the biggest thing to really wrap your head around is the ability to have the parts defined by the models. So even when a part comes in and is getting quoting, remember the first portion of the presentation I talked about from estimating to shipping. If a part comes in and you estimate it, and then maybe 2 or 3 months later you get a purchase order, but that purchase order comes with another model. That second model will actually be captured in your product data management system, and that is the one that moves through your entire manufacturing system. That's typical to how it is today, but that first quote that was attached to the first part is now reevaluated and attached to the second part. And having that continuity, that digital continuity through your entire shop, connected to the op sheets, connected to the model, connected to the tools, connected to the programs, that's the digital transformation that we're talking about. And then eventually that's going to work your way up all the way to the smart manufacturers and back into the OEMs. And then on the right-hand side was just enough dimensions. So application for specific schemes. Steve, anything you want to add to anything there before we close up?
No, I think that that about wraps it up. Again, that I can't reiterate this enough, but that main takeaway there, that parts are now defined by their models rather than the dimensions on them. I mean, once you really understand that, it frees up a lot of time that would otherwise be spent on your traditional 2D drawings, and that's huge. I've been doing the overwhelming majority of the parts that I've had machined recently. I've been doing with minimal dimensions in 3D PDFs now, and the speed at which I can generate those PDFs compared to traditional 2D drawings has just been a game changer.
Yeah, probably something that again, worth noting is that it'll affect how you start to model. So instead of cutting a hole and calling it a dowel pin, you'll actually install a dowel pin hole, and using some of those features that are inherent in the software. So again, across other CAD platforms as well, that greatly enables the MBD or the PMI, whatever software that you're in, to recognize those features, and that enables the downstream systems, either the machining side or the inspection side, to recognize those features. On the machining side, it'll see the tapped holes and be able to pull the right tools from the database, and the same thing down with the inspection side. It'll read the tolerances and apply the right tolerances to the right surfaces. So even in this case, we're seeing some holes. I know you glanced over it on a previous presentation. You were toggling all of the socket head cap screws from underneath that base plate. Even if those were put in 2 separate features, you can still combine them and have one annotation controlling them all. So it really does start to affect how you model, and it does affect how you start to dimension things. Again, as Steve was just saying, the computer already knows where the sharp corner is. We would never dimension to a sharp corner when we're doing traditional 2D drafting, but the computer knows where everything is, and thereby alleviates a lot of that work from having to put the human interface on a lot of those dimensions. Steve, any last remarks?
I think we've got the point across, I hope.
Very good. I'll open the floor to some questions and answers, and I thank you all in advance.
Well, thank you, Mitch and Stephen, for that wonderful presentation on model-based definition. And really, describing the value this technology brings to manufacturing. If folks do have any questions, please do take the time to type them in the question section on the GoToWebinar control panel on the right. Just going to open this up to see what we've got.
I'm trying to do the same.
So it looks like we do have actually a fairly long list of questions here. The first one here that I see is Creo 7 currently does not do a great job of converting software readable PMI to step 242. Does SOLIDWORKS do a better job with that?
I don't have too much experience with Creo, but our interface with SolidWorks so far is that it's doing a pretty good job with converting everything out of again, it's native. We haven't seen any loss of data. Let's put it that way. We haven't had any problems with capturing the PMI and downstream systems.
Another question that came up here is that can SolidWorks show dimensions from the feature and sketches instead of recreating them all?
Yes, you can actually, if you're modeling in such a manner that you know that those features are going to wind up in the drawing, yes, you can actually use some of those features. There is not a direct link to use a feature as MBD, but you can import them downstream. I know that sounded a little bit confusing, but I was going through something in my head. You are able to import model dimensions into drawings. You can do the same thing with MBD. To answer your question, yes.
From the human readable needs, are you using a viewer on the shop floor or 3D PDF?
Right now we're using both. We're using 2D drawings also. Some customers are using 2D drawings. They're taking 3D PDFs and printing them off as drawings. We have customers that are doing all various degrees of integration. So in some cases we're putting MBD onto the model, and then we were printing them in 2D drawings, very similar to what they typically would do. We also have customers where we're putting MBD out and then we're putting it on 3D PDFs, and then they're printing the 3D PDFs, and that's what they're using on the floor. And then one supplier where they can take the 3D PDFs directly onto the floor, in which case they're either doing it with a tablet or they're doing it with a computer.
Okay. Can you speak to the culture shift challenges that you faced?
Yes, it is a huge culture shift. Colin mentioned it earlier. We mentioned it on a previous slide. Ron mentioned it earlier. It truly is a paradigm shift, and it really does take a bit of cultural shift, very similar to ISO 9000, where you needed management support. That is really the most important cultural shift to have, is management that vision, understanding that it's a strategic business decision, and then continuing to support that. It's going to take it's going to take time and resources. The bigger the company, the larger the shift. Some companies may be a little bit more agile. It's challenging for IT. It's challenging for engineers. Maybe less challenging for engineers. It's definitely challenging for the folks on the floor, getting used to working, similar used to do, but then also having to adapt to what's forthcoming or what's coming down the pike. In many cases, we're able to help them, make that bridge, and we're kind of doing it in various phases, very, very slowly. And either in departments, easier to start in the tool room because it's a known start and stop, versus working across the entire organization. We have a tendency to prototype things in the tool room, and then we work our way through engineering back into production, so to speak.
I'll just in the interest of time, I'm just going to read off one more question, but I do welcome you to continue to type in your questions, and we'll jot them down here and make sure we get them answered. So I'll just read this one last one. Have you worked with software readable PMI and PC DMIS or Calypso CMM automatic coding?
I haven't done anything with Calypso. We've been working with PC DMIS. We're working with Hexagon, and yeah, so far the PMI is legible, and we're working both CMMs and with structured light. Seems to be going pretty smooth so far, but we have a lot of support from both the customer and then from Hexagon as well.
Okay, great. Appreciate Mitch, you answering those questions. We're going to move on to the closing portion of this.
Thank you.
So we have opportunities for defense supplier companies to participate on technology demonstrations. If your company has had at least 5% of your sales in one of the last 5 years that ultimately benefited the Department of Defense, we do welcome you to apply for these no-cost demonstration projects. And I'll list the website in the next slide. But these demonstrations are intended to be presented, so preferably we're looking for non-ITAR or export-controlled projects. Otherwise, we'll work with you to identify components of the project that can be recorded and presented. So specifically, we're looking for we're seeking more project applications for the additive manufacturing pilots. Companies that are really exploring additive manufacturing or would like to be introduced to the benefits of additive manufacturing are invited to submit an application for this no-cost technology demonstration. Some of the applications that additive manufacturing is a great solution for include lightweighting, things like assembly consolidation and geometry optimization. Complex parts that fit within an 8-inch cube that have long lead times or are expensive to produce would be prime candidates. We have extended the date to apply to June 30th. Additional opportunities for free 60-day trials of artificial intelligence using Stanley X's DPOW training and upskilling tool are available. If you are interested, please do apply by August 20th. We are scheduled to launch the 60-day trial by mid-September. We have a number of technology demonstrations coming up over the next 2 months. The first one coming up is on July 13th, 12 to 1. We will be presenting a case study using machine tool probing on CCAT's Mazak machine. On July 20th, 12 to 1, Stanley X will present the results of the pilot projects underway using their AI-driven DPOW platform. Then on July 27th, 12 to 1, Spherogen will present the results of the augmented and mixed reality pilot projects underway with 2 companies. And then on August 10th, 17th, and 31st, 12 to 1:30, the results of the additive manufacturing demonstration projects will be presented by CCAT and our technology partners at the Berkshire Innovation Center, University of Maine Center for Additive Manufacturing of Metals, and the Vermont Technical College. The presentations on these technology demonstration projects are meant to illustrate real-world applications of these technologies, what challenges in manufacturing these technologies help to address, how the technology was applied between different pilot projects, and what the outcome was. So we do welcome you to register to attend these presentations at ccat.us/NERDIC. We did want to make you aware of this great opportunity for manufacturing companies. The U.S. Air Force desires to expand the U.S. supply chain capacity to manufacture small turbine engine parts. These are engines that produce less than 2,000 pound force of thrust. The goal is to reduce cost and delivery schedules for existing suppliers and stand up additional suppliers, including from non-aerospace industry sectors. We welcome you to visit sep.ccat.us for more information and to apply for consideration for this program. With that, we'd like to thank you for taking the time to join us today. We hope the presentation and really the great questions that were asked help you to understand the benefits that model-based definition brings to manufacturing. If you do have any further questions, please do feel free to contact us, and we'll be sure to get your questions answered. With that, thank you again, and have a great rest of your day.